The regular replacement of old railway tracks with new ones is an exciting change that enhances safety, speed, and travel experience. On June 21, 2012, the powerful 2TE10MK3024 diesel locomotive hauled a heavy freight train along the Bryukovetskaya-Timashevskaya route in Krasnodar Krai. Operating on the North Caucasus Railway, this train carried essential industrial goods, demonstrating the locomotive's strength and reliability in handling demanding cargo transportation tasks across long distances. The train moves steadily along the railway line, carrying loads of concrete sleepers and crushed stones. Its long formation includes various wagons filled with essential track components. As it progresses, the train maintains a constant speed, ensuring materials are delivered along the route. The entire convoy advances smoothly through open landscapes and curved sections, showcasing its role in large-scale rail replacement projects. This continuous movement highlights the train's efficiency in transporting vital construction materials without interruption. Two workers are engaged in cutting the rails using a metal cutting tool, evident by the visible sparks generated during operation. They carefully position the cutting device onto the rail and proceed to slice through the metal, effectively detaching the old track segment. Once the rail is cut, the removal process begins. A specialized machine, mounted on a railway wagon, is used to lift and relocate the dismantled track section, which includes both the rail and sleepers. This machine is equipped with a large gantry crane system designed specifically for railway construction or maintenance tasks. The gantry crane securely grips the old track segment and raises it from its original position, clearing the way for subsequent replacement operations. In the Panerai Pusinis project in 2017, a massive red railway crane is employed to dismantle old railway tracks. The machine travels steadily along the existing tracks, pausing to lift and remove worn-out rail segments. As it advances, its lifting arm secures the rails and raises them cleanly from their fixed positions. These rails are then set aside in a designated area for disposal or recycling. Nearby, railway workers carefully supervise the process, ensuring each step is carried out precisely and safely. Their presence highlights that the operation is part of a broader railway infrastructure upgrade. The crane's smooth movement and powerful lifting capability allow for the efficient removal of long, heavy rail sections without damaging the surrounding components. Coordination between the machine and the crew ensures continuous progress along the line. The dismantling operation not only clears the way for installing new tracks, but also reflects the use of modern mechanization in maintaining and upgrading vital railway networks. A rail-mounted excavator equipped with a grapple bucket is used to remove old and damaged rail tracks. As the machine moves along the railway, it grips and lifts each worn-out rail section. Instead of placing them beside the track, the excavator directly places the rails onto a railway flat car. Each rail is carefully stacked on top of the previous one, forming an organized pile on the flat car. This stacking process continues as more rails are removed, ensuring efficient loading and transportation of the old rails away from the site for disposal or recycling. The replacement process begins with the detachment and spreading of the rails. A specialized track renewal train, equipped with automated dismantling systems, removes the fastenings, bolts, and clips that secure the rails to the old concrete sleepers. Once detached, hydraulic mechanisms carefully spread the rails apart, creating sufficient space for removing the worn-out sleepers. The next step involves the removal of the old concrete sleepers. These are lifted mechanically and transferred onto a conveyor system that runs along the length of the renewal train. The conveyor directs the old sleepers into dedicated wagons for disposal, recycling, or further processing off-site. Once the sleepers are cleared, the ballast underneath is excavated and cleaned. The ballast, which is the layer of crushed stone that supports the track, is passed through a screening system that separates reusable material from fine particles and debris. Clean ballast is stored temporarily or redistributed onto the track bed, while waste material is collected in separate wagons for removal. New concrete sleepers are then precisely positioned along the track. They are delivered from supply wagons and placed using robotic arms or gantry cranes. Each sleeper is carefully aligned to ensure consistent spacing and level positioning, which is critical for track stability and safety. After positioning the new sleepers, the previously spread rails are guided back into their original alignment. The rails are gently lowered onto the new sleepers and secured with modern fastenings, including resilient clips and anchor systems. If necessary, newer rail segments are installed to replace worn or outdated sections, further enhancing the quality of the renewed track. Finally, the ballast is tamped and compacted around the new sleepers to restore track geometry and ensure long-term durability. This continuous and synchronized operation allows efficient and rapid renewal of railway infrastructure with minimal service interruption. The specialized train begins by detaching and spreading the rails using automated systems that remove fasteners and bolts. This allows access to the old concrete sleepers, which are extracted and transported away via conveyor belts to dedicated wagons. Next, the ballast beneath the sleepers is removed and screened to separate reusable material from waste. Clean ballast is then returned to the track bed. New concrete sleepers are accurately laid beneath the rails using mechanical arms. Once in place, the rails, often newer and slightly upgraded, are brought back into alignment and firmly secured onto the new sleepers using fresh fasteners. This precise and continuous operation ensures a stable and modernized track foundation, improving both durability and ride quality without halting rail service for long periods. First, a crane is used to lift and remove the old rails from the track bed. These outdated rails are detached from their original fastenings and carefully hoisted away, making space for the installation of new components. In areas where the ground is soft or prone to collecting water, workers take extra measures to prepare the surface. They compress and level the ground to ensure stability, then lay down a steel mesh to reinforce the foundation and prevent future deformation due to moisture. Once the surface is stabilized, pre-assembled concrete sleepers, already fitted with metal fasteners, are placed directly on the steel mesh. These sleepers are evenly spaced to match the required track gauge. New rails, pre-attached to the concrete blocks, are then positioned on top. At the connection points between rail sections, workers align the ends and secure them using strong bolts. They tighten these bolts thoroughly to ensure a solid and reliable joint. To fill the gaps between the sleepers and around the rails, crushed stones, ballast, are added. These stones are carefully selected for their size and shape to provide maximum support and drainage. They are spread evenly to eliminate empty spaces and create a stable track structure. Importantly, small expansion gaps are left between rail ends. These gaps are critical because they allow the steel rails to expand and contract in response to changes in temperature, expanding during heat and contracting during cold without bending or cracking. Chinos. For seamless connections, a thermite welding process is used. Pre-installed steel molds are placed around the rail joint. A high-temperature gas flame heats the area, and a container filled with thermite welding powder is ignited. The molten metal flows into the mold, fusing the rail ends together. After cooling, workers grind down any excess weld material to produce a smooth, continuous rail surface. This comprehensive process ensures that the newly installed rails are strong, precisely aligned, and capable of withstanding the stresses of daily rail traffic. The old and damaged rails are first removed using a rail saw. After cutting, a crane mounted on a track reclamation vessel lifts the separated rails and stacks them for transport and disposal. Next, an excavator levels the gravel bed, ensuring a uniform surface for the installation of the new rails. The crane then carefully lifts the new rails and places them on the prepared track bed. Workers align the rails precisely, ensuring that the joints of adjacent sections are perfectly aligned. After confirming the alignment, workers place rail splice plates on both sides of each splice, securing them to the rail ends. Bolts and nuts are then installed and tightened to hold the splice plates in place, ensuring a strong and continuous connection. This meticulous process ensures the structural integrity and smooth alignment of the newly installed rails, ready for safe and efficient train operations. The specialized train is equipped with a lifting system to handle new rails. Robotic arms carefully lower the stacked rails from the flatbed cars onto the prepared ground beside the track. Each rail is gripped securely, lifted, then smoothly positioned with precision. Workers guide the rails into temporary storage positions, ensuring they are aligned for future installation. The process repeats systematically, with multiple rails offloaded in sequence. Once on the ground, the new rails remain neatly arranged, ready for the replacement phase. This operation ensures safe handling and efficient preparation of materials for the upcoming track renewal. The installation of railway sleepers by a track renewal train in a fully automated process. At the front of the train, old rails and sleepers are first removed. Next, the machine smooths the ballast bed to prepare for new installation. Once leveled, new sleepers are automatically positioned onto the bed, followed by the laying of new rails. The components are precisely aligned and fixed in place during the same continuous operation. Throughout the process, workers monitor the system and perform manual adjustments when necessary, such as removing sleepers that cannot be extracted by machine. After installation, final tasks include welding the rail joints and conducting test runs. This integrated method ensures a high level of accuracy and significantly reduces construction time. The simultaneous execution of removal, leveling, and laying makes the process highly efficient. The automation also decreases reliance on manual labor and helps lower long-term costs while maintaining quality. This technique is used for both upgrading existing tracks and constructing new ones, offering a streamlined solution for modern railway maintenance and development. The Caterpillar CAT 320DL excavator is equipped with a dedicated sleeper placement attachment instead of a standard bucket. This attachment has multiple clamps designed to grip the sleepers. The operator lowers the excavator using the clamp arm and lifts it up. During operation, the excavator operator carefully moves the machine along the rail bed. The attachment then lowers and places the concrete sleepers in the designated location precisely. The clamp opens and drops the sleepers onto the prepared foundation one by one. After placing a set, the excavator moves forward and repeats the process. Using this dedicated setup allows the machine to handle and place sleepers quickly and efficiently. This method significantly increases productivity in railway construction and maintenance by reducing manual labor and speeding up installation. The combination of the mobility of the CAT 320D and the specially designed accessories ensures consistent alignment and spacing of sleepers throughout the laying process. During the weekend in May 2012 at Alvesjo, Bain Service carried out 2 turnout replacements and installed 100 meters of new track. A large rail placing machine was used to handle the process. First, the machine removed the old switches. Then, it carefully lifted and positioned the new turnouts, one EUIC 6115 and one EUIC 61 minute 18 seconds and 5 milliseconds into place. Following that, the machine installed 100 meters of new track. It used heavy-duty clamps and lifting arms to accurately grip and transport each rail segment. Working with precision, the machine laid each section onto the prepared track bed. A wheel loader assisted in transporting the rails and other materials to the site. The whole operation was conducted within a 39-hour track closure window, requiring efficient coordination and continuous operation. The machinery's ability to handle both the turnouts and straight track lengths ensured a smooth and timely installation process. A drilling machine first drills a deep hole into the ground to prepare for pile installation. Then, the Movax DH25 hydraulic piling hammer is used to drive the concrete foundation pile into place. This method ensures proper depth and stability, especially when vibratory methods cannot achieve sufficient penetration. The replacement process begins with laying a geotextile fabric over the prepared subgrade. This fabric stabilizes the railbed, prevents mixing between soil and ballast, and improves drainage. Once the surface is covered, workers use specialized equipment to begin installing new rails and concrete sleepers. A large yellow gantry crane, mounted on rail cars, plays a vital role in this task. The machine travels along the track, lifting heavy sleeper blocks from transport wagons and precisely placing them onto the geotextile-covered foundation. This mechanized system significantly speeds up the installation and minimizes manual labor. After the sleepers are set in place, new rails are positioned on top of them using the same crane or additional handling equipment. Workers assist in aligning and adjusting the rails to ensure correct placement and gauge. The entire process is streamlined and efficient thanks to the use of advanced machinery and well-organized material staging. By mechanizing key steps, the project achieves higher accuracy, improved safety, and reduced construction time during the replacement of the old railway infrastructure. The rail welding process begins with a worker using a handheld cutting and grinding tool to mark and cut the damaged rail sections. These may include worn, cracked, or bent segments which must be removed to ensure the quality of the welded track. The cutting creates flat, precise edges on both sides, allowing for an accurate alignment before welding. The Schlatter AMS-60 flash butt welding machine is then used to join the rail ends. This mobile unit aligns the rail ends both horizontally and vertically with minimal tolerance. Using high clamping force, it presses the rail ends together, while an electric current generates intense heat, causing the metal to melt and fuse. Throughout this process, the AMS-60 continuously maintains alignment, ensuring a strong and seamless weld. The machine's mobility allows it to be mounted on various vehicles or integrated into container systems, making it suitable for both high-speed rail lines and heavy-duty freight tracks. The flash butt welding technique used by the AMS-60 is known for producing highly reliable joints, making it a preferred solution in demanding railway applications. The thermite welding process used to join railway tracks, this method relies on an exothermic chemical reaction between metal powder and metal oxide, typically aluminum and iron oxide, to generate extremely high temperatures that melt steel and form a durable weld. The operation begins with preparing the rail ends to be joined. These ends are precisely aligned and tightly clamped in position. A sand mold is then installed around the rail gap. This mold creates the cavity into which the molten steel will flow during the welding process. Beneath the mold, refractory materials are placed to contain and shape the molten metal. Next, a crucible containing the thermite mixture is positioned directly above the mold. The mixture is ignited using a magnesium starter. As the reaction initiates, it produces intense heat reaching up to 2,500 degrees Celsius, resulting in the formation of molten steel and aluminum oxide slag. The molten steel flows down through a tap hole in the crucible and fills the mold cavity, fusing with the prepared rail ends. The slag remains at the top of the crucible and is later discarded. After the molten metal is poured, it is left to solidify and cool naturally. This cooling period ensures the formation of a strong metallurgical bond between the two rail segments. Once the weld has solidified, the mold is removed, revealing the rough welded joint. To finish the process, a specialized rail grinding machine is mounted on the track. This machine grinds the weld area to restore the rail's original profile and ensure a smooth, even running surface. This step is crucial for eliminating any height or alignment deviations at the joint, which could otherwise cause vibrations, noise, or damage to passing trains. Thermite welding is especially advantageous in field conditions where traditional welding equipment may not be practical. Its portability, independence from external power sources, and high weld quality make it ideal for railway maintenance and track extension work. The entire process from setup to grinding ensures a strong, seamless, and long-lasting connection between rail segments, contributing to the safety and stability of modern railway systems. A worker uses an angle grinder to grind a section of rail track locally. Wearing full protective gear, including safety glasses and ear protection, he begins by placing the grinding wheel against the side of the railhead. The grinding process creates a visible stream of sparks as the grinding wheel removes metal from the surface. The worker carefully and methodically moves the tool back and forth along the worn or damaged area, smoothing out uneven spots and restoring the rail shape. This operation focuses particularly on the top and side corners of the railhead, where the contact stress from the train wheels is highest. The grinder is operated in a steady, controlled motion to ensure even material removal without creating flat or sunken spots. During the process, the worker stops occasionally to inspect the surface and adjust the contact angle. This type of manual rail grinding helps maintain the integrity of the rail, reduces the risk of cracking, and extends the life of the rail by preventing further wear and fatigue. A tamping machine lifts the railway track and vibrates tamping tools to compact and align the ballast beneath the sleepers. This process levels the track and ensures proper support. The machine systematically moves forward, adjusting and packing the crushed stone to stabilize the rail structure and improve track geometry. During winter, unloading rails from a rail transport train involves several steps to deal with snow and cold conditions. First, snow is removed from under the steels device to prepare it for operation. The steels device is used to separate and unload the long welded rails. Once cleared, a fixed steel rope is inserted through the device and pulled manually across the length of the rail car. The rope is attached to the ends of the rail strings called whips, using special clamps. Next, the rail whips are pulled forward out of the rail cars using the rope. Only one pulling device is needed for every 3 cars. The rope is tightened, and the rails are gently dragged forward. After reaching a distance of about 90 meters, the train stops for final positioning. The short train keeps the rope under tension to control the rail movement. Once the rails are pulled out, workers remove the remaining fastenings. The steels device helps guide the rail section smoothly to the ground. Workers ensure the rail lays within the correct clearance area. They also remove snow and ice around the unloading zone to avoid damage or misplacement. Crushed stone and snow are cleared using shovels when needed.
метров. А остановочка 91, постоим.
1222, не разгоняемся.
Начинаем выгрузку.
1222.
Смотри, куда вот уходит.
Плети укладываются в цел. Отправляются в желоба.
This efficient method allows safe and accurate unloading of long rails even under harsh winter conditions.